At the start of every lesson, it's important that you plug your USB into your robot. You'll be working with your files on the USB at all times, never saving them to the Raspberry Pi itself. It is your responsibility to make sure that every member of your group gets those files towards the end of the lesson. When you first open up your Raspberry Pi, you'll have to open the Thonny Python IDE. And that's this one down here. And basically this is a programming tool for programming Python. It's quite a nice one. It takes a while to open the first time, and I like to do a few things before I start. The first thing I'm going to do is I'm going to maximize it to full screen. The second thing I'm going to do is I'm going to go to Tools, Options, and make sure that line numbers are on. Okay, you can see that now I've got a line number there. That's always helpful. And the final thing I'm going to do is I'm going to save it to my USB, even though it's an empty file. And the one I'm going to do today is the first one, the LED activity. So basically going to go save. And I'm going to make sure it's onto my USB. So if I go to the main folder here, I can find my USB in Media, in Pi, and I should be able to see the name of my USB. My USB is called Store and Go. So I'm going to put Store and Go there. You see I've already got one Python file on there. Just ignore these things here. And I'm going to call mine LED Basics, which is the name of the first activity. Before you begin this practical experience, you'll need to download the MR5 motordiagnostic.py file from the LMS and store it onto your USB. Once you load that onto your USB, you should be able to put your robot on the floor and run the motor diagnostic program. When you look at the motor diagnostic program, you'll see that in the shell down the bottom, it gives you some instructions as to which pin is actually set to high and therefore which motor should be moving. You'll need to record that information as it loops around, and once it's done you can press stop. Incidentally, looking at this particular diagnostic program, it is not a good program to use to try and understand how to use the motors in GPIO 0. There is a better way which we're going to go through right now. The result of your diagnostic should be that you record some results. For mine, it is pin 6 will move the motor on the left hand side in a forward direction. Pin 13 moves the motor on the left hand side in the reverse direction. Pin 19 moves the right hand motor in the reverse direction, and pin 26 moves the right motor in the forward direction. Your values will be different here. You need to record your results. Once you've recorded your results, you can create a new file, and we can start by creating this particular code. If you'd like to just type it in now, you can, but I'm going to go through and explain each section for you. In the first section, we're going to import the correct functions from the GPIO 0 library. So for example, we're going to import the robot function, and from time, we're going to import the sleep function, which we've done before. Once we've basically got the robot installed or the robot function installed, we can create a control variable for our robot. Your control variable in this case will be MR5. You can change that to be any name you want. For example, you could call it Cecil if you so desired. Either way, once you use that control variable, you can then control the robot accordingly. You'll also notice that my numbers left and right match the recording that I did from the diagnostic. The basic movement functions are fairly straightforward. You basically type in the control variable, in my case MR5, dot forward, open and close brackets, and the robot will begin moving forwards until you tell it to do something else. In this case, it's going to sleep for a second, so it's going to move forward for 1 second, while then the motor will start to move backwards for 1 second. Then it will turn left for 1 second, then it will turn right for 1 second, and that will continue until you receive a keyboard interrupt or a stop. At the time you achieve a keyboard interrupt or a stop, you type in the mr5.stop command, which is a really important command for movement. Otherwise, the robot will continue to move after the program's running because those GPIO pins will still be set high or low according to what happened in your software. The GPIO or the mr5.stop command or the control variable.stop command will basically reset all those pins so that you don't have those problems. You can vary the speed of your motors by typing in a speed parameter inside the brackets for each one. In this case, the speed is 0.5. Speed can be any number between 0 and 1, 1 being full and 0 being off. You'll find that your robot will not start below a certain threshold, usually around about 0.3 or 0.4, depending on your robot and the strength of the motors and how much friction is there on the day, and if there's a piece of fluff in the robot, that sort of thing. So basically you need to experiment with the smallest or slowest speed you can get your robot to go. The fastest speed you'll be able to get your robot to go will be 1. You'll notice that the robot never drives straight, particularly the faster ones. The faster robots definitely don't drive straight. You can try to correct this by using the curve underscore left equals a number between 0 and 1. You can also use the curve underscore right equals a number between 0 and 1 to stop it from going in the other direction. This is going to be a matter of trial and error, and I've found that the curve for going forwards and the curve for going backwards can be different, so you might have to do different corrections according to the directions that you're going. In order to get satisfactory in this, you'll have the robot drive in a 1 meter by 1 meter square with sides that are as straight as possible. You might do this by making the robot drive slow, or you might do this by having the robot drive with the curve underscore left or the curve underscore right function. To get commendable, you'll have the robot drive in a circle of about 1 meter diameter. My hint for this is that if you have one motor moving forward faster than the other, your robot will drive in a definite circle. You'll have to use trial and error to figure out how to make it move in a 1 meter diameter. To get exceptional, you need to create your own custom function that allows the robot to drive for a given distance in centimeters. For example, I'm going to use the drive cm, open bracket, close bracket function, and if I put in the number 45, it should drive a distance of 45 centimeters. If I put in the number 72, it should drive approximately 72 centimeters, with maybe a 5 centimeter sort of variation therein.